Waveguide junctions, directional couplers, part 2, series on microwave engineering, lecture number 1.19. Different types of directional couplers give different levels of performance in their functioning. It all depends upon the design. If the design of the coupler is based on sound principles, then the performance of the coupler is going to be good, very good, even it can be excellent. Performance of directional couplers, it is specified, it is mentioned, it is indicated in terms of two parameters or two indices. They are coupling factor and directivity. In the present session, these two parameters are introduced and explained after giving a formal definition to them. Directional couplers are microwave junctions widely used in industry as well as research fields, more widely than any other microwave junction. They are used for power measurement. They are used as power monitors. They are used to find magnitude of reflection coefficient over the line, that is as reflectometers. They are used to arrest, to reduce, to eliminate fluctuations in the power levels. In addition to performance indices, in the present session, we also focus on different applications of directional couplers in microwave engineering. Now let us move further into the core session. We begin the session with the performance indices of directional couplers. As already mentioned, these are two in number. One is coupling factor, another is directivity. Sometimes isolation is also used. Now we are going to have a definition, a formal definition for these two parameters. These definitions, they are with respect to certain port numbering. That port numbering is shown here. The port that is left side at the top, it is given 1. Usually port 1 is meant for giving input, connecting source to the directional coupler. Opposite to input port, there exists a port that is output port or through port. Here it is given number 4. Below input port, there is port. This is decoupled port. It is given 2. Opposite to decoupled port is there a port which is given number 3. Notice in numbering the ports here, anti-clockwise direction or sense is followed. 1, 2, 3, 4. Better have this port numbering in mind while going through the definitions and the discussion on performance indices. Coupling factor, it is indicated by capital C. It is a measure of power being sampled from the incident wave. Formally, it can be defined as ratio in dB of the incident power fed into the main port to the coupled port power when all ports are match terminated. Mathematically, C in dB is 10 log Pi by Pc. This mathematical statement is in terms of powers. It can be converted into a form which involves scattering parameters. In such case, C becomes equal to minus 20 log S31 magnitude. It is not difficult to understand the connection between these two mathematical defining relations. Here, Pi is the power entering into the coupler. Pc is power delivered to the matched load at the coupled port. These powers are to be considered only when the remaining two ports are match terminated. While the coupling values of 6, 10, 20, 30 dB are quite common, several devices are available with coupling values of 13 or 16 dB etc. up to 60 dB. Before going further, just to remind the important aspect of coupling factor, it is a measure of the power being sampled from the incident wave. Some power is flowing. A part of this power is diverted. How much of the main power flow is diverted? That is indicated by coupling factor. Another index performance index of directional coupler is directivity D. Capital D is symbol for this parameter, for this index. It is a measure of how well the coupler differentiates between forward and reverse traveling waves. It is a measure of isolation obtainable at the coupled port with the power being fed into the main line at through or output port. Formally, it can be defined as the ratio in dB of the power output at the coupled port when power is transmitted in the preferred direction to the power output at the same port when the same amount of power is transmitted in the opposite direction. This defining statement, it gives lot of information pertaining to the parameter directivity. However, the power output at the coupled port when power is transmitted in the opposite direction is same as the power output at the decoupled port when the same amount of power is transmitted in the preferred direction as the coupler is reciprocal. Since the requirement is to have as little reflected energy as possible coupled out of coupled port, the values of directivity are usually high in the range of 25 to 40 dB. Under ideal conditions or for an ideal directional coupler, directivity tends to be huge, infinity. Directivity can also be defined as the ratio in dB of the power output at the coupled port to the power output at the decoupled port when all the ports are under matched termination condition. Mathematically, D in dB is equal to 10 log PC by PD. This power ratio, it can be converted into ratio involving scattering parameters. In such case, D becomes equal to 20 log S31 magnitude by S21 magnitude. The derivation or connection between power's definition and S parameters definition. It is simple, it is obvious, it doesn't require any explanation. Here PC is power delivered to the matched load at the coupled port. PD is the power delivered to the matched load at the decoupled port. These powers are to be considered only when remaining throughput is matched terminate. Another index, another performance indicating parameter is isolation. Mathematically, isolation in dB is defined as 10 log Pi by PD. It can be expressed in terms of scattering parameters to as minus 20 log S21 magnitude. From their basic definitions, an interrelation between these three performance indices can be established as I is equal to C plus D. Now, an important aspect pertaining to directional couplers. For that matter, for any device, specifications play a key role, an important role in giving information pertaining to their quality of functioning. Now we consider key specifications of directional coupler. In addition to the three that are mentioned above, that is coupling factor, directivity, isolation, SWR, standing wave ratio, bandwidth, frequency sensitivity, insertion loss, power handling capability, they are also key aspects, critical aspects of the directional coupler which indicate the performance levels of the coupler. A typical set of specifications appear as directivity 35 dB minimum, coupling 10 or 20 or 30 or 40 or 50 plus or minus 0.4 dB, frequency sensitivity plus or minus 0.4 dB maximum, SWR 1.05 maximum mainline and 1.10 maximum over secondary line. By looking into the specifications, one can easily get some idea regarding the performance level of the coupler. They are also useful in selecting appropriate coupler for the application on hand. If the application demands a coupling of 20, one can go to a coupler which gives a coupling of 20. If the application requires a coupler of 40 dB coupling, then one can go for coupler with a coupling of 40. So specifications, they are useful to the user in several different ways. Here are shown applications of directional couplers. Two most important applications of directional couplers. In A is shown application of DC as power monitor. In B is shown DC application as part of reflectometer. Now we consider power monitor application. Power monitor does two things. One, it indicates continuously whether there is a power flow or not. Second one is it measures, it gives the amount of power that is flowing, if flow is there. How power monitor is able to do these two things, we can understand it from the diagram that is given in A. This is directional coupler, 4 ports, port 1, port 2, port 3, port 4. Transmitter is connected to port 1. Antenna is connected to port 4, output port. So this is transmitter of a wireless communication system. Port 2 decoupled port is terminated over matched load. To port 3, a power meter is connected. In typical case, the directional coupler and power meter, it is always in the circuit, 24 hours, 7 days throughout the year. Now, when system is working, transmitter gives out power. This power is usually in kilowatts. It may be even in megawatts. It travels through the main line of the directional coupler and reaches antenna. There it gets radiated into space. A small part of this power flow in the main line, it is sampled. Maybe 1,000th power in the main line is, or maybe 1/10,000th of the power in the main line may be sampled. And this power which appears at port 3, it is fed to a power meter. Power meter then gives an indication. From its deflection, from its indication, the amount of power that is flowing from transmitter to antenna can be estimated. If the transmitter is working, then there exists deflection in the power meter. So deflection in the power meter ensures that transmitter is working, and the amount of deflection gives an indication, an estimate regarding the power that is being flown from transmitter to antenna. So this setup that is being displayed in A, its functionality is two-dimensional. That is indicating the presence of power flow and also giving an estimate of the amount of power flow. This setup is called power monitor. One can notice in the power monitor arrangement, the role of directional coupler is a critical one. Let us move to another application. The setup pertaining to this application, it is shown in figure under B. The purpose of this arrangement is to find reflection quotient. Only magnitude can be determined with this setup. Signal source is connected to port 1, load is connected to port 4. If the load ZL is equal to characteristic impedance of the line that exists between port 1 and port 4, then there will not be any reflection from the load. Otherwise, a part of the incident wave gets reflected. Net result is when ZL is different from Z0 over the main line, there exist two waves. One wave is called forward wave, incident wave. Another wave is called reflected wave. A part of the forward wave is sampled and it is available at port 3. A part of the reverse wave, it is sampled, it is diverted. That power is available at port 2. The ratio of reflected wave to incident wave is reflection quotient. To be precise, ratio of voltages in the reflected wave to incident wave, it is reflection quotient or magnitude of reflection quotient. Because of same amount of sampling, magnitude of reflection quotient over the line, it becomes equal to magnitude of the ratio of the waves that appear at port 2 and port 3. That ratio is obtained with the help of ratiometer. Ratiometer is fed by the waves at port 2 and port 3 after converting them into voltages with the help of detectors. Detector DR, detector DF. Output of detector DF is a voltage which is proportional to forward wave amplitude. Output of detector DR is a voltage VR. It is proportional to the amplitude of the reflected wave. Ratiometer calculates the ratio of these two voltages. Its deflection indicates magnitude of reflection quotient. This is a description, an explanation of the functioning of reflectometer in most general terms. Now a few points regarding power monitor. In this application, the meter at port 3 samples a portion of the transmitted power. The transmitter and the main load, in this case a radiating antenna, are connected to ports 1 and 4 respectively. The coupler value is chosen so that practically all the transmitter power is delivered to the antenna port. Typical values are 30 to 60 dB range. With a perfectly matched load at port 2 and infinite coupler directivity, the meter reading is independent of antenna reflections when Zg is equal to Z0. What is Zg? It is impedance, internal impedance of the source. When the directivity is infinity and gamma 2 is 0, gamma 2 is reflection quotient at port 2. The transmitter output power Pt is given by this formula. Pt is equal to Kc P3. Here Kc is coupling. P3 is power at coupled port. Pt is power fed to the antenna. The power meter can be calibrated to give the transmitter power output directly. Now we move to reflectometer. In this application, the directional coupler is used to find SWR, of course its magnitude, by measuring the magnitude of reflection quotient due to an unknown load impedance. In the circuit arrangement, the signal source is connected at port 1 and load impedance ZL at port 4. Detectors DF, DR connected to ports 3 and 2 sample the forward and reflected waves respectively. They convert the waves into voltages. The DC voltages out of the detectors are directly proportional to the microwave power levels at each port. Assuming identical detector sensitivities, VR by VF is P2 by P3 is equal to B2 by B3 whole square. Notice VR is output voltage of DR. VF is output voltage of DF, detectors outputs. These are voltages. These voltages are proportional to powers incident over them. So input to the detector is power, output is voltage. And detectors are devices which obey square law. Their output voltage is proportional to incident power. From that particular aspect, this relation has come into being. Of course, from P2 to P3 ratio, one can easily come or reach to B2 by B3 ratio square. The ratio meter takes the square root of VR by VF and displays it on the meter. The scale ranges from 0 to unity since it represents the reflection quotient magnitude. Reflection quotient magnitude varies from 0 to 1. It cannot be more than 1. Therefore, the scale, it has readings from, or it has numbers from 0 to unity. The meter can as well be calibrated to give the SWR directly. The meter reading is accurate only if the coupler has infinite directivity and the detectors are perfectly matched. Assuming identical detectors, the ratio meter reading M is equal to square root of P2 by P3. P is power at port 2, P3 is power at port 3. Another application of directional coupler is in signal leveling. DCs are also used for signal leveling, which is virtually mandatory in swept frequency measurements. Even though sweep generators with leveled outputs are available, an external closed-loop method of leveling is usually resorted to eliminate the impact of random behavior of components between the generator and the test piece. Such a leveling loop can be conveniently arranged through the use of a directional coupler and a detector. These are some of the things which I want to share with you right now. To recap, In the present session, in the session which is to be concluded, our focus is on parameters or indices which indicate the performance of directional coupler, coupling factor, directivity, and sometimes isolation. Then we moved to important applications of directional couplers as power monitors, as reflectometers, and also in signal leveling applications. Hope you have a wonderful, a fruitful, a successful, a beautiful, enriching learning experience. See you soon. Bye bye.